Okay, and then give them like 2 more minutes. So I'm not going to start a peer deck today because we're going to be basically working on a sequence of examples. Um, because, well, I guess I'll just to illustrate what we saw before. I'll go ahead and open not the peer deck, but just the slides from last time. Maybe I will. There we go. Okay. Uh, so we did free fall, we did forces, and we looked at analyzing forces in one dimension. I think it's the last thing we did. And our two main things that I want us to keep in mind are we've still got this scenario of comparing equilibrium versus non-equilibrium. So equilibrium means zero net force, which means we have uniform motion, which means constant velocity. Or if it's not in equilibrium, that's to say there is a net force, then the velocity must be changing. There must be an acceleration. And so our analysis is of the form of determining whether the net force points one way or the other, and then using that to make inferences about the forces. So, for example, when we had the rock sitting on the floor, we know that weight was pulling down on the rock and normal force was pushing up on the rock. And since the rock is just sitting there, then what does the net force need to be? Zero. And so the total up forces have to match the total down forces. Whereas with the rocket, we're going upward and increasing speed. So velocity is upward. If we're increasing speed, what direction does acceleration have to be? Positive. Exactly. So also pointing the same way, basically, right? Velocity is positive because we're moving upward. So to speed up, we need uh, acceleration to point the same way, and so that's also upward. So when you apply the forces to this, so we have an upward force due to the exhaust, so we could call that a thrust force, or an applied force, either way, but we have that upward force, and we have two downward forces. We have weight pulling down on the rocket, and we also just have air resistance, trying to keep the rocket from moving through the air. But since we're increasing speed, the total number of boxes up, tick marks up, needs to be more than the total down. So I think in this class, in this period, I think we did 6 tick marks up for the applied force and 2 for the weight and 3 down for the drag. The actual numbers don't matter. What matters is that 6 was bigger than the 2 plus 3 pointing downward. Okay, I'm gonna have to send attendance. So there we go. And so we're going to apply that to solving some example problems. So for now, we're still going to worry only about one-dimensional motion. And so we're only going to be doing up versus down or right versus left. And you'll see that as we do some examples. I've added a new template so if you go to our course materials under templates, 1D force problem is what we're going to be using right now. So you can make a copy of that. And a lot of the steps are very similar to the steps that we had for kinematics problems, but some of the details are different. So, for example, instead of making graphs of position and velocity and acceleration, I'm asking you to draw a free body diagram, which is where you put the dots and everything. Um, and oops, didn't mean to have. Here, let me uh, fix this a little bit. Thank you. I'm going to get rid of the giant one that I didn't intend to be there, and I'm going to go ahead and put little dots on our starting points. There we go. That way we know, well, that we have a dot. It's not, don't have a lot to add there. But anyway, so now this should apply to any new copies you make. And so let's just start with a problem. I'll just give you a problem and we'll work through it together. Let's see. You have a spring that hangs from the ceiling for some reason. Don't worry about why. You attach a um what is a thing you could attach to a spring? A watermelon to the spring, which causes it to stretch by say 12.5 centimeters. First of all, let's go back here and figure out the mass of a watermelon. What do you think? Mass of a water molecule or watermelon. So, yeah. So I was gonna guess 5. I guess that's on the smaller end. We'll do 7.5. Why not? 7.50 kilogram watermelon. Don't worry about how you're attaching it to the spring. You just do. What is the spring? Oh, uh, when it hangs motionless. I'm just trying to highlight the fact that it's just hanging there. What is the spring constant K of the spring? Okay, let me make everything a bit bigger for readability. Maybe too much. There we go. Okay. All right. Well, we're going to go through our sequence. Um, and this is our first step. So we're going to draw just a simple image. So here's the ceiling. And we need to draw a spring. Spring is always the hardest thing to draw in Google Drawings. Trying to find just a cheat that I can use. It looks close enough like a spring, but what if that's not terrible. So I'm gonna draw the spring like that, and just for clarity, talking about the stretch, I'm going to draw it again and put a watermelon on it. And we can tell it's watermelon, of course. Ooh, that's too bright. That's too bright. Well, the tone of these don't look right though. It needs more saturation, but darker tone. No, not dark enough. It is very important that you get your watermelon colors exactly right. Well, it looks better on the picker. You know what? That's fine. Okay. Uh, and I'm just going to draw again. This isn't strictly necessary. This is for demonstration purposes for the class that the amount of stretch that is occurring is this extra distance here. And so I'm going to call this, well, delta L is what I would like to call it, but it's hard to get a delta in the text. Capital delta. Oh, oh, all right, fine. So be it. Okay, I'm going to zoom back out a little bit. Okay, so our assumptions, we don't actually need any assumptions in this case because it doesn't matter if there's air resistance because it's sitting still. It doesn't matter if there's friction because it's sitting still and it's not against a surface. So this is one case where we can just move on past that. We do want a free body diagram for the watermelon though. So first, do we want the up-down axis or the left-right axis? Indeed, exactly. So we're just going to delete the other one, and then we can apply our force vector arrows to this. So I'm actually going to come back over here. All right, I hate that. Automatically fills the width. You know what? I'd almost rather. Oh no, I can't do it. This is just a stupid hack so the width doesn't get crazy. Um, okay, so let's talk about the forces on the watermelon. And remember, the tile chart means type, agent, and object. So what are the forces on the watermelon? There's gravity. So I'm going to call that weight. And what's the agent? The earth, right? The agent has to be a physical thing with mass. So it's the entire earth that's pulling down on the watermelon. And what's the object? The watermelon. And then what else? Could our what happened to oh no, did I kill the picture? Oh. But it was so beautiful. Well, anyway, imagine the watermelon. There's got to be at least one more force here, or the watermelon is not going to remain motionless. What is pulling up on the water? The spring. So our symbol for spring force was just F with a subscript SP, and the agent for the spring force is always the spring. And what's the object? Watermelon. Okay. Is there anything else? That is it. Just those two. So if it's motionless, and those are our only two forces, uh, I'm going to go ahead and draw one. I usually draw weight first, just because I know um, it's always fixed by the environment, right? It's always going to be due to the planet that it's on, that the object is on, and so I don't have to compare it against other factors. Right? I am going to color code my forces. Also going to page break this so it's together. So we'll make those purple also. And what direction does the spring force go? Up. And how many tick marks should the spring force be? Whoa. So, I'm still regathering my bearings here. The creepy shining twins over here. Okay, so I was going to count this as 4 tick marks down. If you go by the little marks. So what does the net force need to be for the watermelon to hang motionless? It needs to be the same. Exactly. So if it's hanging down by 4, the spring has to be pulling up by 4 so that the net force is 0. Sure. Just for you. Watermelon green. Okay. So this step of the free body diagram is, I won't say the most important step. You know what? I'll just say it's the most important step. Getting your head right about the free body diagram sets you up for getting the right equations. And then it's a matter of algebra getting from the equations to the answer. But the physics step is getting equations from looking at the free body diagram. So any known values, we'll go ahead and put in our known values here. We know that the mass of the watermelon, I think, was 7.5 kilograms. We said that the stretch of the spring, I think, was 13.5 centimeters. Do I need to convert any units for any of these? I want them to be in SI units. Exactly. So the base units for mass are already kilograms, so we're done there. But centimeters we want to convert into meters, and so 0.135 meters. I think that's all the given. I'm sorry? It's 12.5. Oh, it was 12.5. Thanks. In 1D, we don't actually need this at all, so I will delete it from the template in a bit. And then these are equations that relate to the different forces that we have equations for. We haven't talked about this yet. This is drag. I've only hinted at these. This we've definitely seen. This is the equation for the magnitude of weight. And this we just very briefly touched on last time, which is the amount of spring force. So we're not going to need these 3 equations in this problem. We only need the weight and the spring force. And then we're going to start looking at Newton's second law. We're only dealing with the vertical direction, so we don't need the x one. And the left-hand side of this equation, I wrote it out like this on our slides last time. If we're talking about the net force in the y direction, which by the way, this is just another way to write the net force, because what does the sigma symbol mean? Sum. Exactly. So this is the sum of all the forces in the y direction, and that's the same thing as the net force in the y direction. We're going to go through all the forces. Any of them that are pointing upward, we're going to add. Any of them that are pointing downward, we're going to subtract. There's not a whole lot of them to go through, but we will go ahead and do that. So what force or forces point upward? Spring. So we're going to have just that. And what force or forces point downward? Weight. And so we're going to have weight with a minus sign. And that we can write out as MAY because it's true. But we know something about AY in this case. What do we know for this watermelon that is stationary? 0. It's 0. And this is something we had already concluded from our free body diagram, or during the time we were working on the free body diagram, right? This is where we decided the net force is 0. and therefore the total boxes up for spring had to be equal to the total number of boxes down for weight. And that is to say, if we take one and subtract the other, we'll get to 0. So once we have this, we're going to look through to see if we have any equations for any of the forces. In this case, we have an equation for each of the forces. And so we can substitute that in. So for the spring force, we're going to have K delta L, where delta L is the amount of stretch. And we're going to subtract mg from that, and that's going to equal 0. What is it we're trying to actually solve for? We want the spring constant, and I've even reminded you the symbol for the spring constant. The spring constant is this value right here. It tells you how many newtons the spring will pull for every centimeter you stretch. In this case, we haven't figured out all the numbers yet, but we basically know the amount of force and the amount of stretch. So we're just trying to get that constant out of it. So how will I solve for K? Exactly. Let me make these bigger. Now everything on the right is something that we know. And so now we can plug in our values with units every time, right? So we know the mass was 7.50 kilograms. We know that G is, remember in this equation, G is the magnitude of gravitational field strength. So it's the magnitude of the amount of gravity. So it's always a positive value. So we have 9.80 newtons per kilogram. I'm going to write it as. And then we divide by the amount of stretch, which is 0.125 meters. So can I do that one in my head? 75 times 800 minus 200 is 600-ish. 612 newtons per meter. I went the wrong way. I did the 2% correction up instead of down. Get rid of my question mark now. So there it is. That's the answer. You can paste it down there if you want. So that is, broadly speaking, the type of approach that you're going to take. I'm going to give you another one now that's going to be broadly similar. Before I completely give you that though, let me wanted to get rid of this from the template. And you know what? I'm actually going to do something else real quick. There. This is the one. That way we don't have to worry about the actual Google dot, which tries to grab your arrows. So minor thing, but should make it a little bit easier. I'm also going to put a bounding box around it so that we don't get that horrible zoom effect if uh, if you delete one of them. Okay. Get a little bit more. Okay, so that was just to clean things up with the template a little bit. So now we're going to open a new one. I'm going to give you a problem. I'm going to give you some time to work on it with one another, which will be great for video. Maybe I'll pause during that. Okay. You are bungee, is that how you spell bungee? Jumping um, over the buffalo. Uh, the cord is originally, what's a good made up length? Was long, but um, after you jump, the longest it gets is uh, what's a good number? They seem to stretch a fair amount. I'm going to say 15.0 meters. You have a mass of um 77 kilograms. What is your acceleration when you reach the bottom of the path of the bungee jumping? Bottom of the, what's a good noun? How about we say the lowest point in your bungee jump? Well, why did you like that one but not that one? Isn't this one a bird? Or an American video game company? It's really the only one, huh? Right. Okay. Um, I'll go with you so far as the picture, just so you can tell what it is that I'm trying to say. If it's not clear so far from the statement. So, we're gonna have the Buffalo River, which actually doesn't directly show up in the problem, but I'm gonna go ahead. And then we're gonna have a a bridge that people have made over the Buffalo River purely for the purpose of bungee jumping. And then the bungee cord is originally 10 meters. But that's not with you hanging on it or anything, right? That's just if you lower it from the top and it was just hanging there, it would be 10 meters long. But as you jump, I'm actually going to draw an intermediate figure also. When you're at the lowest point, you're like that. And this is when it's at its longest. So this is when it's at 15.0 meters at max stretch. And 10 meters at zero stretch. I guess I don't really need an intermediate uh, figure. Oh, I do, however, need. Thank you. Actually, a way I'm going to give you a necessary piece of information is to have one more intermediate figure, which is when you're at the end. And you're waiting for them to pull you back up, then the bungee cord is going to be 12 meters. Okay, so this part is basically what we just did with the watermelon. So if you get to be the watermelon and you're just at the end of the spring hanging out. But this is only after you've been waiting there for a while when you're at this stage. What would happen originally is you jump, you go way down, stretches, stretches, stretches. Eventually, you turn around and come back up. When it's at that max stretch, is when I'm asking the ultimate end of the question. But you will need the spring constant, just to make it clear. You'll need the spring constant. To get the spring constant, you'll need this. So if the bungee cord is originally 10 meters long, but it's 12 meters long if you're hanging at the end of it, what would you use for delta L? 2 meters, right? And then in that case, the pull, the amount of force on it, would be just the weight of you. So this would be exactly the same. There's no picture of watermelon over here anymore. It would be exactly the same as watermelon. This middle part is different because you're not stationary at that point. Your velocity is 0 for an instant. You don't actually need to use that in any way in this problem. In fact, I don't even have to tell you that this is the maximum stretch. I would just need to tell you at some point it's 15 meters long. Tell me the acceleration. And it would be the same number whether or not you're going to stretch more later or not. Okay, I'm going to give you time to think this over. I will add this part in text. Okay. Any questions at this stage? Okay. Um, I recommend you talk to other people in your vicinity or cause there to be people in your vicinity if there currently aren't any. I'm going to pause the recording for people who are watching the recording. Yes, we're okay. So let's pick up some things, make sure we're in the same ballpark. So if we're looking at the free body diagram, in particular, we will eventually especially want the free body diagram at this stage. But if you want, you can draw one for this stage also. But let's together talk about when we're at the 15 meters, so the maximum stretch. Um, so what is it that is experiencing all of these forces? The person, right? So that is going to be our object. Right? And of course, this is, I just made that worse. I should send it to the back. and lock it. Can I lock it? Whatever. I just can't make this the way I want it to be, can I? Oh well. So tell me about those forces. What force do we have up? What force do we have down? Okay. So I'll have spring go up and I'll make it, I think I made it 5 tick marks just for a number. And I'll go ahead and add that to the TAL chart. And again, TAL stands for type, agent, and object. And so the type of this first one is spring force. I'm getting there. There we go. And the agent of the spring force is exactly the bungee cord. And the object is the person. And I'm going to make that purple just to color code it with my free body diagram over here. And what else do we have? We have weight, and of course weight points downward. What can you tell me about the number of tick marks for weight? So let's say that it's more for a moment. So I guess I can leave it black, that would still work. I'm gonna go ahead and type this in. We have weight, and the earth is the agent like we talked about for the watermelon. Okay, so if we have, what did I choose? I should have chosen nicer even numbers so I could see them easily. So 4 tick marks for the bungee. Should the weight be fewer than 4 tick marks, equal to 4, or greater than 4 tick marks if we're at the lowest point that we're going to be, and we're about to spring back up?
So is it going to stop for a second?
It is going to stop. The velocity will be 0 for a moment. But is the acceleration going to be 0 there? No. How do we know the acceleration is not going to be 0? If the acceleration were 0 and their velocity was 0, what would happen to them? What would happen for their motion? What's that? They wouldn't move, right? But they are going to be moving back up. So, does that mean we need the spring force to be larger or weight at that point? Yeah. Because it is going to be pulling them back upward. So I've made the weight 3 down and the spring force 4 up. And just to highlight that, I'll write this under here. The net force is upward because the person is about to bounce back up. And just to add more details, their velocity is momentarily 0. Actually, it's not literally momentarily. Momentarily means for a moment of time in English. So we'll say instantaneously 0. But it will not stay 0. Okay. So there are basically 2 steps that we're going to have to solve with the forces. So first, let's just go ahead and put in what we know. So we know the mass of the person, did I say 77, I think? And we said that delta L at the end, compared to the final value, I guess, is 5 meters. And again, that's because we're looking at the change in length compared to its normal length, its unstretched length. So we have the 15 minus the 10. That's how we got that. Okay, but this alone is not going to be enough for us to figure out the acceleration. And we can see why. Let's go ahead and do a couple more steps and we'll see exactly why. I'm going to get rid of these three equations since we won't need them in this problem. I'm going to move back out a little bit. And then just like with the watermelon, we're only dealing in the vertical direction, so we don't need that one. And if we apply our upward forces minus downward forces, what force or forces point upward? Spring is pointing upward. And what about downward? Weight. But for this problem, we don't know what AY is. That's in fact what we're trying to find. So if we solved this for AY, yes.
How do you get the under subscript?
If you insert equation, so it's insert, then symbols, then equation. And you press a letter, and then you shift underscore, and we'll make a subscript. You can do it without the equation also. And it's either control period or control comma. I just try each one until I find it. So control comma was the subscript. Oh, okay.
Sorry, I have a problem with that. Oh.
That's funny, that is different. And the way I'm getting to the equation editor, it's with the hotkeys. So you press Alt-I, that opens the insert menu, and then see how Y has a little underline? You press Y, and then E has a little underline, and you press E, and you can type in the equation.
Okay, thank you.
Okay, so I'm typing probably more lines than are strictly necessary here. I'm just trying to show you the reasoning. But this is as far as we're going to be able to get at this point, right? Because we know delta L, that's fine. We know M, we know G, we still know M, but we don't know K automatically. So to get K is the reason I gave you this extra information. I'm not going to tell you exactly how right now, because it is the same as what we did with the watermelon. So I'm going to, hopefully we're caught up to the same place. If not, definitely ask me. And we'll see what kind of final answers people get in a little bit. Okay, so what have you all figured out about the spring constant? If anything.
Isn't it mass divided by
Close, very close. Right, so if we refer back to the watermelon situation, right? So in this one, the watermelon was in equilibrium, right? It was no longer moving up or down, it was just sitting stationary. At a degree of stretch, my picture got deleted. I say that in a passive voice way, so I don't have to admit fault. But at that point, the only two forces acting on the watermelon are weight pulling it downward and spring force pulling it upward. Right. So when we look at our equation of motion, our Newton's second law, we have spring force pointing upward, weight pointing downward, so far, that's pretty much the same thing as we had over here with our bungee cord. The only thing is, in that scenario, when it's sort of at its equilibrium length, the net force is 0. And so that's what we did with the watermelon is we went ahead and plugged in our forces, and we made sure that the delta L that we used, of course, in this problem I only gave you one delta L, but that delta L corresponded to the watermelon hanging motionless. And then it was just a little bit of algebra to solve for K there. So if we want to use that over here, what values are relevant? Equation and what values?
The equation for weight, and then so it'd be the mass and the gravitational whatever, and then the delta L while you're like not moving.
Exactly, right? So this equation is actually true the whole time if there's no air resistance. In the cases I'm giving you in those two states, there's no air resistance. But overall, of course, there is as you're bouncing up and down and up and down, up and down, and gradually coming to slowing to a stop. But this, excepting for that air resistance, this is Newton's second law the whole time. So if we just take this equation and write it for hanging motionless equilibrium, we've got this still, but we know that this is equal to 0. And our equations that we plug in, for our spring force, we have the K delta L minus mg is equal to 0, where, like Violet was saying, the delta L here is just I think I made it 2 meters. It's the 12 meters minus the original 10. And so we can solve this for K. And so we get 77.0 kilograms times 9.80 newtons per kilogram. And we divide that by 2 meters. We get something. 377.3 newtons per meter. And we can just double check the units here, right? So G is in newtons per kilogram. We're multiplying by kilograms, so that gives us plain old newtons in the numerator. And then we divide by meters, so we're left with newtons per meter. I don't know. Oh, I put a comma. Newtons per meter. I'm going to actually cut and paste this up here. So this K, this is a property of the bungee cord. So it's going to have, just like it would be for a spring if you had a literal spring instead of a bungee cord. So this K is going to go in for here, and this was the only thing we didn't know out of this. So let's look at all of these values and figure out what we need to plug in. So this K is what we just found, 377.3 newtons per meter. What is the delta L that goes with this situation? 5, exactly. 5 meters. Our mass is 77.0. And then G is 9.80 newtons per kilogram. And then the mass is 77.0 kilograms. Did I make this big enough? Yes, I did. Like by a lot. me know when you have final number for that.
14.7.
14.7.
And then it works out to meters per second.
Exactly. Yeah. I'll just kind of write down here to show you how the units worked out. Right. So in the top we have just plain old newtons. Right. So if we had newtons per meter times meter, that gives you newtons. You have newtons per kilogram times kilogram, that gives you newtons. So the numerator has newtons, the denominator has kilograms, and the definition of a newton is a kilogram meter per second squared. And so if you divide that by kilograms, you get meter per second squared. So that's our final answer for this. And we just need to double check if the number makes sense, right? So the main thing is the sign of the number. So we ended up with a positive acceleration. Is that what we would expect? Yeah, because we're being pulled back upward, right? Our velocity had been negative, it's about to be positive, and so there's an overall change in velocity pulling us upward. Any questions? Okay, so I'm going to give you some practice problems. And my anticipation, well, we'll just see. My anticipation is that on Friday and Thursday for 4th period, we're going to have a lab, but I have to double check that it makes sense for where we are. So, if there are no questions, you can go ahead and go, and I will see you on Friday.
Was there another one of you guys that this you guys did?
Yeah, I'll link it on.
Okay.
So these I keep not really like pointing these out, but if you go to the modules for our given chapter, I am posting at least sometimes the slides and the notes, and this video will also be posted on there.
Okay, and then do you have to explain them both about tonight?
Not even by tonight, probably by tomorrow night.
Okay.